supposed to be a cold winter according to NASA. The sunspot the minimum, but we shall see. Theoretical predictions are not always fulfilled, as observers were telling. And one other thing that came out in the news this week is that the ALMA observed a particular supermassive black hole environment and found that there is evidence for a fountain in it, where material that accretes onto the black hole seems to go up and then fall back into the disk, which was a phenomenon predicted in theoretical calculations of accretion disks prior. I remember some 25 years ago looking at numerical simulations that showed that material without the viscous transport of angular momentum comes close to the black hole, then gets up and falls back on the disk. So these kinds of behaviors were expected, but I guess they see it observationally now. And next week at 3 p.m. we will have a winter party where we'll all socialize and talk about science and not science with each other in this room. So mark your calendars, 3 p.m. a week from today.
So our first speaker is a professor of physics at the University of Gothenburg, Marek Abramowicz, and he's going to be speaking to us about signals from alien civilizations with the best title page I've yet seen.
Thank you very much. I'm sorry for my voice. I came to Harvard from Oxford, and I've got the English flu, so I will be speaking with this funny voice. It's not my normal voice. All the illustration which I show you of Daniel Mróz, who is still alive, and he was a famous illustrator of novels of a Polish science fiction writer Stanisław Lem, of whom most of you probably heard, or maybe you've read his stories. The most famous one is Solaris. Tarkovsky made a movie based on this novel. So I tell you now, today, about how we, and I will explain who, we are, believe alien civilization will signal their presence for the rest of the galaxy. And I will try to convince you that there is just one way of doing this. One smart way. Clickable table of content. And why they would care to signal their presence. Of course, we don't know, because we only know us, the humans. And we, the humans, have this metaphysical needs of signaling our presence to other civilizations, like we have done it recently, but also it is something far longer than our times. Egyptians put a lot of effort to kind of signal their presence to other civilizations different than they. And this is an example of a general principle which was recently stressed by Abi, that we are looking for that civilization. If we ever discover signs of our civilization, that most probably this civilization is already dead for a long time. Like,
is there historical evidence that the Egyptians were thinking of signaling other civilizations?
I will not answer this question because I have only half an hour. After my lecture, I will be happy to discuss this with you. Sorry. And there are two opposite views about the number of this alien civilization. Why? One by Giordano Bruno. Not only him, but he is the best known example of saying that there should be plenty of civilizations in the universe. And then Enrico Fermi, who was, I think, the first who very seriously asked whether perhaps there is only one, meaning us, that there are no other.
But the one on the left was burned on the stage.
Not for this. he was a kind of general nasty heretic, and he was not for this. He didn't believe in the virginity of Merek.
That's all.
Not only, there are several other things. So he was burned not because of this. The church at the time didn't care much about science. He committed much more serious. And Fermi's view touches. Of course, the Drake equation didn't exist when Fermi formulated it, but there is the conflict from kind of a naive view that there should be plenty of civilization. I will not explain the Drake equation for you because it's very well known. But we never found any traces of them, no matter how we were searching for them. So the question is, if there are so many of them, why we do not see any direct or indirect proofs of their existence? And there are basically two answers to this Fermi paradox. One, that it is really genuine, that there is a very small number, and this small number may be even one in our galaxy, of the technically advanced civilizations, for the reasons which we're discussing in this book and by many other people, namely that Earth is very unique. First of all, our galaxy is a unique galaxy. It's not active. Then our place, solar system place in the galaxy is very unique. It's in this Goldilocks region between 7 and 9 kiloparsecs. And if it would be in closer in or farther out, the life as we know it, our life, would not be possible, etc., etc. There is a list, like planetary orbits should be stable, and it is a big issue. We have large moon, which seems to be very crucial in the emergence of intelligent life on Earth. And also our atmosphere is stable. All the simulations of the global climate on planets similar to Earth show that there is a collapse of atmosphere. So it is either like on Mars or like on Venus, global warming and globalizing at a time scale which is a small few billions of years typically too. And of course, to life to emerge, our life is 4.5 billion. So Earth, from this perspective, is very special. But there is another point, namely that is time axis and space axis. Civilizations are short-lived and separated So if it is one and another one, all the signals from here will not reach this one. And that is a typical situation in between civilizations, that we are missing each other because we are probably, this we don't know, short-lived and separated. And then suppose that this is a lifetime, like here, of a civilization, and this civilization is building some artifact, some spaceship, something with a practically infinite lifetime. So then we can find it. And searching strategies should take this into account. So the first strategy is discovering some object, some material object, direct contact, like these crop circles. Okay. And let me tell you a story about crop circles. But Mom, it was proved that crop circles can be made with a board and a rope. But who tells you that the aliens cannot use a rope anymore? So there are no evidence, as everybody knows, of a direct contact. Also, there were a lot of excitement, always, starting from Kepler, who wrote Kepler, wrote the first science fiction novel, short novel about the voyage to the moon. Martian attacking us. That was Orson Welles' radio broadcasting on October 11th, 1938, and there was a panic in the States reported in all newspapers. I took this figure from the internet and I discovered it is something interesting. Yes. It was less than 1 year about the breakout of the war. And at this particular day, the Germans pushed away from Germany all the Jews who had double citizenship, Polish and German. And they went to Poland and survived, but only for a few years. So maybe this panic was kind of anticipation of what it will happen really. And of course, thank you. Looking for these artifacts comes to this category of direct contact. Space jump. Some people say we should look at it. And it was excitement that maybe we found one. But then of course, unsuccessful. Optical searches, Dyson spheres, for example, unsuccessful. Radio searches, SETI, unsuccessful. So then, why not gravitational waves search? And that is our idea, and our means go back. These three colleagues work at Meudon, Eric Bourboullion, Odele Straub, and me. So we think that a super intelligent, technologically advanced civilization would put an object of the mass of Jupiter at the east orbit around Sagittarius. And of course, just by orbiting, mass orbiting, will produce gravitational waves. And these waves, if such an object is now at the orbit of east orbit of Sagittarius, can be picked up by LISA easily. So we suggest that LISA should look at this signal. Because Ramesh cannot loosen this up. At no additional cost, if we discover this signal, then it would be a great news. If you would not, then
How do you know that it's not natural? Sorry.
Also, Marek, how do you keep it there? Because it will fall, won't fall it. That's coming in the next.
15 minutes.
No, you're running out of time.
Half an hour I was told.
That's including discussion.
So,
There'll be no discussion.
There's no discussion, okay.
no,
I guarantee you.
I will make it shorter. I
No,
will
no, it's
answer
okay. Go ahead.
during my talk. I will
Go ahead. Yeah.
because these are exactly what you ask. How do you know that it is not? How do you know that it's artificial? And how you keep the object at the orbit? That's exactly 2 points. And there are 2 papers, both in preparation. One is a serious paper on gravitational waves and has nothing to do with alien civilizations, just calculations. And a serious paper, not yet published, or in preparation, about the idea. So, we call this object a messenger. And specification of it is like that. Location must be unique and obvious to everyone in the galaxy. Signal must be fundamentally artificial, not something like peep, 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 peep series of prime numbers, but artificial fundamentally. You see it and you know that it cannot be natural. Lifetime should be at least a small few billion years, because if it is shorter, then we are not gaining anything, because it is like all other kind of signals. And as Ramesh noticed immediately, there should be energy supply to keep this object going, and this energy supply should come from a natural source with no need of service, because then few billion years, nothing later. And then the question to ask is, will LISA pick it up? So these are serious calculations based on solving the caustic equations up to the 10 L equal 10 harmonics. And for the Jupiter mass, the energy output for the Schwarzschild black hole would be two times 10 to 26 Hertz per second at ISO. Now, signal to noise ratio calculated by solving the same equations. And it is, I will not go explaining all this. Anyway, it is that integrated over 1 year, it gives signal to noise ratio 190, which can easily be picked up.
It's the frequency or
how frequent?
No, what's the orbital frequency?
Orbital frequency is 10 to minus 3 hertz.
Ah, very good.
Of, of course, that's very good, which I will tell. This frequency is fixed by the fact that the orbit is ISK. Okay. It's the frequency at ISK. And as you see, we calculated this for several different Kerr parameter A and for several different inclinations, because at the moment we only know precisely the mass of Sagittarius, but we don't know A or inclination. But when they finish this Arizona week, and Maciej Wirgus and other colleagues are back here, they will tell us what he say from Event Horizon Telescope. Okay.
They
So
will know what is A, they will not tell us.
I see. Yes. Eventually you will.
Eventually they will.
So we will know this in a very precise way, the frequency. And orbital stability, that is your question. So using quadrupole formula, we may calculate how quickly an orbit will decay if there is no supply of energy from outside. And data formula for lifetime and frequency change. So that is the time of decay Jupiter was, 10 to 5 years. And you may say, then you will never know whether it is artificial or not, because we cannot wait 10 to 5 years. But the thing is that there is a frequency change. And this frequency change, in terms of hertz per second, is 10 to minus 16. And we do observe routinely such frequency changes in millisecond pulses. And from this very rough calculations, we concluded that if the signal is integrated in 5 years, we can observe this frequency change. So 5 years, LISA is looking at Sagittarius at this particular frequency of gravitational wave. And if the frequency doesn't change in 5 years, then we know that it is artificial. Fundamentally, we know this fundamentally, and I'm not joking. That is the most serious point here. That if we observe this frequency and it is stable over 5 years, then we know that it was done artificial. That some people some beings who had this advanced technology.
Marek, one more.
Yes.
There is accretion of gas. Is the friction on the gas too small compared to the drift in frequency here?
I do not. My memories are fading. We discussed this, and I think that because I do not remember this, the answer is that friction. I'm not answering your question. I don't know. I know that we were discussing this. And because I do not remember the answer, I think that it is negligible. But then, of course, for the friction, it doesn't need super intelligent civilization. In this probe B, we have geodesic motion. We, the humans, constructed, as everybody knows, a satellite, which has is inside a sphere, and there are servo motors, and they are measuring the distance to this sphere So the thing inside moves on an exact geodesic. Although there is friction of whatever kind you can imagine. So this is the answer. If friction would be a problem, then that is not a big technical problem. And then just 10 to 3. It goes exactly where it should. The sensitivity. So how could it work? And what I told you till now is based on geodesic motion, calculation of gravitational waves, solving those equations, solid stuff. And this is a faculty that the energy output is 10 to 36 erg per second. And if one has a rapidly rotating neutron star, and it is slowing down, then in a time of a few billion years, it can supply this power output. So there is a natural way of feeding the needed energy to this messenger. If the messenger would be of much greater mass, like if it would be one solar mass messenger, then the total energy integrated over this, say, 3 billion years, translated into mass, would be 10 to 5 solar masses needed. So that obviously is not possible to anybody in the galaxy. I'm sorry. Therefore, Jupiter mass is just the ideal mass for the purpose, because it is sufficiently large to excite LISA 8 kiloparsec away, and not too big that there are natural processes to which can supply this energy. So Dyson sphere or something capturing this energy, laser beam to the place. And this, of course, should be far away, because if it is close in, then it will also emit gravitation. There is another problem, namely that if it would be Jupiter, and not an object of Jupiter mass, but Jupiter as it is, then it will be subject to tidal destruction. The density must be 10 to 6 gram per centimeter cube at this orbit to be safe. And of course, the best thing is to squeeze this Jupiter to a black hole size. Job is now nothing. And there was a beautiful book by John Archibald.
Marek, if it is a black hole, that laser beam will simply disappear inside. It won't push it.
There is the whole whole structure around it.
Around your black hole.
Yes.
And how do you match?
This I don't know. Okay.
That's left for future engineers.
I'm not an engineer.
Yeah, right.
Anyway, John Archibald Wheeler wrote a book a long time ago about how we, the humans, can squeeze Earth to a black hole by placing hydrogen bombs all around Earth and bombing. So that is doable. Even we can do it with Earth, which of course is much harder than with Jupiter. So that is not the problem. So, and this is it. So location is unique indeed and obvious to everyone because there is only one center of all the signal. If we or somebody else will be looking for a sufficiently long time, but this sufficiently long time is 5 years, so it is not very long. It will be then immediately obvious that it is that it is artificial. Lifetime of a few billion years can be arranged in a natural way. So there are objects, normal, standard physical objects, and then these will be that's my message. Thank you very much. The names. Eric Gourgourion is the most important one.
Questions from the speaker?
So I would argue that just making a black hole of Jupiter mass by itself is sufficiently artificial because, well, you could have primordial black holes, but we don't know how to make them. And so if you, for example, had just two such black holes in a binary producing the signal without anything else, you don't need neither such test. That by itself would be quite remarkable.
Yes. What's the lifetime of that, though?
Well, it would be even longer. Well, comparable, 10 to 5 years. But if you know how to compress Jupiter to a black hole by itself, you can develop signals that, I mean, for example, you could have eta creep mass from a star. You could have things that look completely unnatural. So far, we haven't seen an X-ray binary with Jupiter mass.
This idea of blowing up the Earth, though, that may happen anyway.
So, Marek, I'm still confused about how you're going to push this black hole. Okay, so you got your Dyson sphere around the neutron star.
Yes.
You collected all the energy, you made a beam, and somehow you have to transfer momentum, or angular momentum, to this black hole to cancel whatever is being lost.
Then I have two beams.
You do whatever.
Like in this Shikarsky computers.
Never mind, but you're going to have, you can't push the black hole. So as you said, you put a structure around the black hole, but you can push the structure, but the black hole will keep going on its own geodesic. You know, why should it feel the effect of your laser beam?
Why not just make the black hole after you pushed it to where you want it to be?
No, but you want to keep it for 3 billion years.
No,
No.
So put the mass there, then make it a black hole.
Ramesh, there is this black Jupiter black hole
Yeah.
around the structure, and this structure has all kind of jet engines, and the power of these jet engines is supplied by this beam.
Good.
Yeah, I know your question.
Yeah.
What I am doing is the momentum.
No. I'm asking, how do you couple it to the black hole?
Gravitation.
You can push a structure, but will it move the black hole?
Gravitation. Can't you do shepherding like you?
No, I don't think so. I would like to see how this works.
I'm not sure whether I really understand your question, but the point is that orbital energy is being lost, and it is just from the most general theoretical point of view necessary to supply the missing energy. How it is done in details, I'm sure that I do not understand the depths of your question, but to me it is a technical problem.
Okay.
You have all these mirror things, and then you can cope with this extra momentum. If you have two beams, for example, then of course if you have two beams and you play with trigonometry right way, then you will cancel them. I know that is not the answer to your question because Okay.
Let's say that we saw this around Sagittarius A star, but then it turns out we also looked at some other galaxy and saw exactly the same thing. Would you then say that it was artificial? That
We cannot see
two
this
different
in other. We cannot see
But
this in
that's
other.
that's a technical problem.
No.
That's an engineering problem.
No,
Just
absolutely.
Just like your.
Because from us, the galaxy center is 8 kiloparsecs only. The other galaxies, Andromeda, etc., are hundreds of millions light years away from us. So the signal,
Hundreds of thousands.
hundreds of thousands, yes, the signal will be too weak.
But if since we're playing what if games with engineering tricks, if we ever develop the technology to do this, and we saw two of these structures, one in Sagittarius A star and one somewhere else, would you then say that they were artificial, or would you say, there's some natural physical process that yields this, and that we just haven't figured it out yet?
Try to avoid this question because I do not see how we can pick up this gravitational wave signal from anything else.
Well, I don't see how
than
we
the
can build a black
neighborhood
hole or another black hole.
our
So.
own galaxy.
I have a question. So
Yes.
even around the center of our galaxy, how can we distinguish this artificial, like Jupiter, black
But
hole?
they are
with
not
some
there.
other-
These intelligent beings are not at the center of the galaxy. They are some other place. They are only putting this messenger there. But they are
Oh yeah, but
themselves.
my question is, why couldn't there exist some like a neutral star, not just black holes, but this is still around the center of the galaxy, but
I mean, natural.
yeah, natural.
Yes, but this I answered already during my talk, that after 5 years of signal integration, we will see the decay in orbital frequency. If there is no supply of energy from outside, any natural piece of matter of natural origin not supplied with energy from outside will spiral down, and of course long time, 10 to 5 years, but we can distinguish a circle from a spiral even if the difference is very tiny in terms of change of the frequency 10 to minus 16.
We better leave it till later. Let's take the speakers. Okay, our second speaker is Nishanth Gudapati. He's a postdoc downstairs in the CSMA. He's speaking to us about gravitational lensing via Finsler geometry.
Right, so thank you very much for the introduction, and thank you all for coming. I'm going to talk about a topic that has both geometric and astrophysical context, and I'll try to find a balance. Just to give you a brief outline of the talk, so I'm going to introduce some notion of geometry called Finsler geometry that is slightly different from Riemannian geometry, and that somehow plays a role in the this physical situation that I referred to previously, and then slowly move on to the physical situation and explain how that fits in and what information can that give in understanding some physical problems. Okay, and it's joint work with Marcus Werner from Kyoto University. Okay. So let me get started with the geometric part. That will be the first part of the talk. If you recall some things about the Riemannian geometry, probably the most fundamental object in Riemannian geometry is the so-called arc length, right? So that's a great and deep idea of Riemann, that you can actually do a lot of geometry, construct a lot of geometric structures from something as fundamental as the arc length, which is a function, basically mathematically it is a function on the tangent bundle of the manifold. What are the basic properties of the arc length? It is homogeneous in this second argument. It's of course positive in Riemannian geometry here. And very importantly, f squared, the quantity f squared, gives us the metric tensor. And once you have the metric tensor, you can develop a lot of deep structures and define the notions of derivatives and so on and so forth that are consistent with that. Right. So the idea of Finsler geometry is to take those rudimentary properties of Riemann, and somehow generalize that. Where we do the same thing. We have a function, a quasi-definite function on the tangent bundle of a manifold, which has essentially the same properties that we discussed before of the Riemannian geometry, except that this condition is slightly different and slightly. It is a situation where that difference shows up in the sense that the metric tensor is not directly f squared, and there is some notion that is slightly weaker than the metric tensor that comes around here. So it is, and it is not some abstract notion. There are some well-known spaces where you can see what it is different from the Riemannian geometry. For example, if you look at the special case of Randers' geometry, you will see that there is certain Riemannian piece there, and it is this part which makes it Finsler.
Sorry, I'm totally lost. Can you explain how the metric is f squared? What is f squared?
It's kind of f squared in Riemannian geometry, yes.
I know what a metric is, but
So-
what is f squared? So
F is the arc length.
I'm familiar with G mu nu. So what's the relationship
in
between?
Riemannian geometry, f squared is essentially gij dxi dxj,
okay.
right?
Okay, all right.
And I'm saying that there is something like that in Finsler geometry as well. I'll discuss more about that, which is basically constructed from the Hessian of f squared, which has some kind of interpretation of a metric, but it's not really like the Riemannian metric. I'll discuss that later. So to discuss some concrete examples of Finsler geometry, so there are some examples there. Of course, you can realize the Riemannian geometry as Finsler geometry as well, where in that case, this quantity will exactly be the metric tensor as well. Okay, so once we have that notion of the arc length, which is slightly more abstract than the Riemannian geometry, what kind of geometric structures can one endow to that arc length function on the tensor, the tangent bundle? Right. So it turns out that you can construct something that is very similar to the metric tensor by taking the Hessian of f squared. If you do that, you'll get something like a metric function, which I showed you. I just wanted to convince you about that. That if you take the Hessian like that, this will be the formula, and if you contract that with two, it has two arguments. If you contract that with an element, with a vector, you basically recover the arc length function squared. And it's not so straightforward in this case, because it's based on our assumption that our f is a homogeneous function in the second argument. How does that show up? So if you have a homogeneous function, there's a theorem for homogeneous functions by Euler, who showed that if f is a homogeneous function, its radial derivative is proportional to the function itself, and the proportionality constant is the degree of homogeneity, which in our case is 1. So therefore you have that. And if you have that, if you differentiate one more time, this quantity becomes 0, and the quantity is basically f squared. So you recover some notion of length by taking the Hessian of the arc length, roughly speaking. And this is, but this is slightly misleading. It's not really like a Riemannian metric tensor, because it is still dependent on y. It's dependent on the direction of y. So geometrically speaking, what we're saying is that if you have a manifold, the metric, this particular metric is in such a way that you define the length of a vector. The length of the vector depends on which direction you look at it. That doesn't happen in Riemannian geometry, right? So the way you define, the inner product doesn't depend on the direction you're looking at. That's different with the Finsler geometry here. That's very fundamental and different. It shows up in further constructions. but there is something like the metric tensor. That's what I want to show here. Right. So let's once we have the in quotation marks the metric. Actually, it's called the fundamental tensor, as I call it. So let me not call it metric tensor. It's called that fundamental tensor.
So can you then go one step further and define something that is really a scalar?
Sorry, could you
Can you
repeat?
then go one step further and define something that is really a scalar? It doesn't depend on your.
Can I define something scalar as?
Something that is really a scalar. I mean, the length in the ordinary geometry is a scalar, right?
So f is a scalar.
But
here.
it depends on, on the.
Yes, yes,
Correct.
but that's something that one would have to live with in Finsler geometry.
So you don't have a real scalar then in this geometry.
Yes, yes. So the most fundamental thing is this arc length scalar on the tangent bundle, and that's all you have. Yeah, and there's nothing more fundamental than that. From that you construct all of these other structures. So if we move on and look at more further constructions on Finsler geometry, you can also define the notion of angle in Finsler geometry, and the way you do it is also similar, has some similarity with the way you would in Riemannian geometry. And the way it's done is that you consider a unit circle basically and measure the arc length of the unit circle. That gives you the angle, right? So how does one do that in Finsler geometry? You basically take the volume form based on this fundamental tensor that I discussed before and restrict that to a unit circle. It's called, by the way, it's called indicatrix in Finsler geometry. You restrict that to this indicatrix and you get the induced volume form and you measure the length, induced length form because it's a surface, and then you measure the length on that unit circle. So that's there's some subtlety with that. You basically divide that with f squared so that you won't make that a scale invariant quantity, but that's some technicality. And likewise, as in general geometry, you can define the notion of covariant derivative if you have an appropriate notion of connection. In general, as you know, in geometry, when you have a covariant derivative, there's one piece when the derivative falls, an ordinary derivative falls on this vector, and one piece where the derivative falls on the way the basis moves itself. So there is there's ambiguity or there's flexibility in defining how you define your connection, but there is a notion of Chern connection, which is a torsion-free, almost metric compatible connection, which I'll discuss later if I have more time. So again, the formula looks very similar to the Riemannian geometry, but then there is this problem with which I've discussed before, that your connection or this Christophel's in quotation mark Christoffel symbols or these connection symbols are y dependent, so it depends on which direction that y is pointing.
Can you use this fundamental tensor to raise and lower indices unambiguously?
Yes, to some extent, yes. There's always this problem with y, but yeah. So one important application of that Chern connection, there are two of them that will come about in our talk and in our work. One is the geodesic motion, which I'll discuss later. The other is this Gauss-Bonnet theorem. So one very nice thing about this Chern connection is that you can recover topological information of the manifold using the Gauss curvature. I put that in quotation marks because it's not really the Gauss curvature of Riemannian geometry. It's the analog of the Gauss curvature that you would construct in Finsler geometry using Chern connection. So the Chern connection recovers the topological information of the manifold. That's really a very nice and powerful thing about that construction, which we shall use in this talk. Okay, having discussed some background on geometry, which is supposed to be one half of the talk, so once I discuss that, so let me provide a context where all of these geometric constructions are relevant and come about in physical or even in particular astrophysical situation. Okay, and where does that show? Where do those things, those constructions show up? It is in the so-called optical reference geometry or optical geometry of a physical space-time. This notion was introduced in part by our previous speaker in this article. The idea is that once you have a solution of Einstein's equation, once you have a space-time, the idea is that we would like to project that space-time onto a Riemannian hypersurface, a Riemannian manifold with a Riemannian metric. In this case, but we'll discuss later, in some cases you cannot have Riemannian, but anyways, in this particular case of static space-times, you would like to project your space-time onto a Riemannian metric in such a way that some important properties are preserved. And why are we doing that? Because in general, if we have a choice, we would like to prefer Riemannian geometry, right? So the idea of this optical metric is that, let's take an example of Schwarzschild. This is a Schwarzschild, and you all know what this phi is. And if you project it in such a way that the metric of this projection, when you go downstairs to the Riemannian metric, is like that, then it has some very nice properties. That is that the null geodesics of your physical space-time correspond to the spatial geodesics of your optical metric. That's a very, very important property. That's a crucial advantage, basically, of the optical geometry. That if you have null geodesics of your physical space-time, they correspond to the spatial geodesics of this Riemannian metric. Mind you, that projection is not really this ADM type projection. It's not really this equal to the constant hypersurface of the ADM. It's slightly different. It differs by a conformal factor. So that's a big advantage of this optical reference geometry. And one important feature of their construction is that once you take the projection in that particular way, which preserves the null geodesics, the resulting optical metric has a throat at the photon sphere of the Schwarzschild space-time. In some sense, loosely speaking, that gives some kind of a topology for the optical metric, which I'll discuss more later. And why are we doing that? So the point is that, as I said, the point is that you would like to use the null geodesics of your physical space-time to map it into your optical space-time and study the geometric behavior of the optical space-time. And one important, in my opinion, very interesting application of the optical geometry is introduced by Gibbons and Werner. What they did is basically characterize many things that occur in astrophysics using the geometry of using optical geometry. One astrophysical situation like that is as follows. You have a source which is emitting energy, like some electromagnetic energy or gravitational energy, and this it follows a geodesic and reaches our observer O. And there is another geodesic that also reaches the observer O. So we're considering a situation in which we have multiple images at the observer coming from the source, and we would like to characterize, for example, the angle at which it reaches our source, and that can be done using the Gauss-Bonnet theorem, and in this domain, and basically allows us to capture a lot of things, capture these observables in terms of the geometric and topological properties of the space-time in which these geodesics are propagating.
So can you explain what the calculation that you'd be doing is? So the normal calculation in the usual geometry is that you solve the geodesic equation, and you have two geodesics from the source to the observer, and you have their momenta at the observer, and you compute the angle between them using the metric. So how are you supposed to do this differently here? What's the alternative calculation?
So the point is, there are two things. So that's one situation. Another situation is to calculate this angle of deflection. So you have this fiducial curve, and you calculate the angle of deflection that's happening due to gravitational lensing here.
But you don't use the same metric, you use a different metric?
Always we use the optical metric. And we use they use the Gauss-Bonnet theorem to basically calculate all these angles. And I'll show you one application, or which illustrates the importance of the optical, illustrates the topology of the optical metric. Notice the following. So for a Schwarzschild space-time, the curvature is negative, right? So if you look at it in terms, because you mentioned the geodesic deviation, if you think of it in terms of geodesic deviation, then the geodesics should not reconverge if the Gauss curvature is negative. But why do they do? Is the question, and it is solved by the topology of the optical metric. So that's the point. So if you look at the application of the Gauss-Bonnet theorem, where the angles are as I showed in my previous picture here, the point is that even though your Gauss curvature is negative, the point is that you're using the topology, as you know, let me briefly take 30 seconds to explain these terms. So this is the Gauss curvature integral. This is the geodesic curvature of the boundary term. And these are the boundary terms that you would get in the Gauss-Bonnet theorem, which are basically the exit angles of a piecewise smooth domain with corners. So the point is that if you consider the inner boundary of the optical domain as this point where as this curve where you have the throat of the optical metric, then this term becomes zero. But the Euler characteristic, as you see, is also zero. So therefore, even though your Gauss curvature is negative, because of the topology, your geodesics are reconverging again. So somehow, the fact that you're observing these multiple images is associated to something that is as fundamental as the topology of the optical metric. So that becomes transparent in this formulation, for example, which in my opinion is very aesthetically appealing, that something as fundamental as the topology of the optical metric captures the fact that you have multiple images at the source. Otherwise, your geodesics should actually diverge because you have negative Gauss curvature. Right? If you think in terms of the geodesic deviation equation. Anyway, so if you look at the other picture, what you can do is you can use, again, the Gauss-Bonnet theorem for this domain and calculate the deflection angle due to lensing. That is the same thing like before, but we basically take this curve and we tend that curve. So this is the source and this is the observer, and there's another curve like that, and you basically calculate the deviation here with respect to some fiducial curve, right? And what you do is basically tend this curve to infinity, which as you know is asymptotically flat, and that is captured by this quantity. And what that gives is a formula for the angle of deflection in terms of the geometry of the optical metric. And if you do that calculation for Schwarzschild, as you can see, you can obtain the relation between the mass m and the impact parameters. So if you have a more massive Schwarzschild black hole, you'll see that you have a more deflection, for example, as expected. So the point of our project is basically to calculate what happens, calculate similar things, basically to capture this gravitational lensing situation as some kind of a topological effect, basically. So that's the idea of rotating black holes. So, in general, if you, as you know, perhaps I don't need to discuss all of that. You know the definition of a stationary black hole, where you have an asymptotically time-like Killing vector field, but interior you can have an ergo region and so on and so forth. And most important stationary solution is, of course, the Kerr solution, which is expected to be the steady-state solution of all the black holes found in the universe, or all asymptotically flat black holes. So the idea is to do the same thing for stationary black holes, or among them rotating black holes, in particular Kerr black holes. There we'll reach some problems. I'll discuss that later. By the way, so that's where our Finsler geometry comes into the picture. By the way, there are other approaches to do lensing for rotating black holes using some modifications of the Riemannian geometry, and also considering the ADM spatial metric as well, not relying on the optical metric as well. But our idea is to capture lensing as a topological effect of the corresponding optical metric. So the point is that for stationary spacetimes, for rotating black holes, the corresponding optical metric is not Riemannian, but it is of Finsler type. That's where the things that are discussed in the first part of the talk come into picture. So the corresponding, in particular, if you look at the Kerr black holes, it is not just Finsler, it is of Finsler-Randers type. In particular, that's the expression you would have for the arc length for the corresponding Finsler-Randers metric for Kerr black holes in Boyle-Lindquist coordinates. Yes.
So you're saying this is a 3D Riemannian manifold, and if I solve the
I basically represented that on the equatorial plane, but you can write that also in 3D. You can make a projection onto a 3D,
So
I wouldn't say Riemannian, but Finsler.
If I solve the Finsler-Geodesic equation in this metric, that's supposed to be equivalent to solving.
That's a very good point. That is where all the subtlety comes into the picture, and I'll discuss more later. So the point, the comment that I made about the correspondence of the null geodesics with the geodesics of the spatial metric in the static case will no longer hold in a strong sense. It will hold in a weaker sense. I'll discuss that later. So, but that's one of the subtleties that one encounters in Finsler geometry. It has got something to do with the connection being y dependent. Connection and directional y dependent. So I'll discuss that later. So what we were able to do is basically generalize that for any stationary black hole space-time. In other words, whenever you have a stationary asymptotically flat black hole space-time, you can project it onto a Finsler-Randers type of a metric as long as you're outside the ergo region. And an interesting point that is relevant for this particular lensing scenario is that it becomes asymptotically Riemannian. That means that allows one to basically capture these things like geometric mass and so on and so forth. That's the idea. Right. So let me briefly discuss what we're doing. Basically,
this is only if the original metric was asymptotically flat.
I mean, it's strictly not necessary, but the point is that we would like to associate, as I showed you in the formula for Schwarzschild, the angle of deflection very conveniently comes out to be something that is proportional to the mass of Schwarzschild black holes. So the point is that we would like to find, ideally, some association of the angle of deflection with the geometric mass of the space-time. So in that setting, it becomes convenient if you consider asymptotically flat space-time. That's the plan. We'll see how it goes. Anyway, so as I said, the corresponding optical geometry of stationary black holes is of Finsler type, and as I said in the introduction, there is a version of Gauss-Bonnet theorem for Finsler geometry. This is basically a generalization of the results of Chern et al. When you have this lensing situation. So the formula that I showed you in the early part of the talk is for a compact manifold, but if you have a lensing situation like that, you have a region with a boundary and with corners, you will have a more general formula like that, where all of these things are Landsberg angles, and this is the geodesic curvature, and so on and so forth. So if you start computing all of these things, and we'd like to calculate, some angle of deflection, which is somehow hidden in the last term there. And if you start computing all these things, in particular, for example, if you consider that for Kerr, you can compute all these things. You can compute the total Landsberg angle on S1 using this isothermal coordinates, and you can also calculate the Gauss curvature in the orthonormal frame, which is basically Riemann R1212 component of the Riemann tensor. But as it was pointed out before, what is very subtle in Finsler geometry, that is something that we're trying to resolve, is that is precisely this point that was mentioned. Let's say we can do the same thing for Kerr space-time. So we can take the equatorial plane, and we can take the inner boundary to be the circular orbiting null geodesic, trapped null geodesic on the equatorial plane, and take that to be the inner boundary. And we would have hoped that this quantity becomes zero because it's a geodesic curvature. It turns out it's a little bit subtle in Finsler geometry because if you take the geodesic equation, if you take the Finslerian arc length and perform the first variation and calculate its critical point, you'll get the geodesic equation. But that is a little bit subtle in Finsler geometry because of the following. In Riemannian geometry, using the Levi-Civita connection, you can parallelly transport your tangent to your geodesic, right? What you get for free is that once you have that, you can take the normal, and the normal is also parallelly transported. So both things hold in Riemannian geometry. So you can take a normal, you can take a tangent to a geodesic and it's parallelly transported, but the normal to the geodesic is also parallelly transported with the same, geodesic. That's something that you get for free in Riemannian geometry. It turns out that in Finsler geometry, that's not the case. So if you have take the critical point of the length functional, you get a geodesic equation that parallelly transports only the tangent of the curve, not the normal of the curve. So that's a problem that's got, again, it's got something to do with the y dependence of these symbols. And that's something, and why is that relevant? Because in this geodesic curvature expression in the Gauss-Bonnet theorem, it is this normal that becomes, it's the normal curvature that becomes relevant. So that's where somehow, even though if you consider a trapped circle inside the equatorial plane, it seems that that term will still remain, even though it's geodesic in some sense. So that's something that we're trying to resolve. Yes.
Can the deflection angle be greater than 2 pi in Formula 15?
That's so. Let's first discuss in the Schwarzschild case. So that's what I was referring to before. The point is that for this formula, let's say we don't have this term. The point is that for this formula to hold, if your Gauss curvature is negative, then there is an upper bound on this. It has to be small, right? For that equality to hold. So this covers the so-called weak deflection angle. So otherwise, for example, you can take, as you know, in Schwarzschild and also in Kerr, you have trapped geodesics. So if you come too close, you become trapped, and the angle of deviation there is like infinity or something. So so if for this picture to hold, one is automatically assuming that there's something called weak deflection. So therefore, these angles are small. Otherwise, this curve will become trilateral and rotate.
So you cut it off with the ergosphere?
Sorry?
You don't go within the ergosphere? Is that the resolution?
The ergosphere, so this is Schwarzschild, so there's no ergosphere.
If you go down to the photon orbit, the deflection angle will diverge.
Yes, so that's why I said. So that's why we assume the so-called weak deflection. So therefore, you only have so there is some massive object, and you have a weak deflection like that. That's it, and that's what this picture. So this is the source, and this is the lens in some sense, and you have a weak deflection, and that is captured by this formula here.
So how do you implement that assumption? I mean, it's just not true for Kerr. So what do you mean you assume that?
I mean, if you're far away from this trapped geodesics, you're far away from, if your impact parameter is high enough, then you don't necessarily have this trapping. So that's the so-called weak deflection assumption. You can also do that. There's also a version of the Gauss-Bonnet theorem if you have self-intersecting curves, probably, I don't know. So, but as it stands, it's a weak deflection construction. So that's what we're trying to resolve, that there is the notion of T parallel and N parallel in Finsler geometry, and this equation corresponds to T autoparallel geodesics. So that's the status of this project in a sense. Thank you very much.
Okay, so we have time for maybe one or two questions. Mark?
I have a question about the reason I'm doing this. So, as you said, in the case of static spacetimes, optical geometry works in a very simple, elegant way. Now, you'd like to have something like this in stationary case, but then you have this weak deflection assumption, which somehow, for an astrophysicist, means that you are so far from the source that the differences between static and stationary case are not that important. If you cannot enter the ergosphere, where there are topological differences between these two cases, are you not, right from the start, losing a lot? So my question is really, to put it in a very brutal way, is it that your program is not ambitious enough?
I mean, the point is that so one can also prove. So this the point is, of course, to start with, to consider the simplest possible case and understand these geometric structures. In particular, what was very surprising and interesting was this thing. To learn this thing was, mathematically very satisfying. That something that you have in Riemannian geometry doesn't hold anymore, and it's actually seems very subtle. That then the question that one may ask is which gravitational functional gives the n parallel equation and so on and so forth. But anyway, to come specifically to your point, this particular projection. So I said so. This holds if one is outside the ergo region, but as long as one does not intersect the ergo region, one is strictly inside the ergo region. This similar result holds as well. So one can prove that it's of Kerr-Randers type inside the ergo region as well. The problem comes with the onset of the ergo region. So potentially one can do that also close to the horizon and so on and so forth.
Because this is where nowadays the strength of optical geometry shows up. You can, for example, calculate ring downs these wavefronts using optical geometry in the static case, and they are pretty accurate vis-a-vis the numerical analytic tricks based on optical geometry in the static case can give us, and they gave us ring downs forms which are
I read that somewhere.
So of course the question for a physicist or astrophysicist, can we do it for a rotating case? And if you have problems with ergo region, then
it's at I don't know if it is strictly inside and close to the horizon, it's still fine. But so that's the mathematical limitation that this quantity here. So this is the quantity in Kerr-Randers structure that determines the whether it's a Finsler or Randers structure or not. This quantity doesn't behave well at the ergo region, at precisely the point where.
Is it this capital H here, GPT? The normal
capital H there.
What is the capital H?
Maybe it's not exactly GTT, so I think it's this delta function which gives us the minus a squared sine squared theta. So that's the exact formula of that H there. So so at the ergo region, the Finsler-Randers structure doesn't hold, but inside that it does hold. So maybe potentially one can try to apply these things. But as I said, one starting with the most simplest case.
I understand this, that when we do something new, we start with the simplest case.
Yes.
Yes, that's the problem. So we better defer further questions till afterwards. But let's thank our speaker. Oh yeah, of course. So we're going to be taking. Are you feeling well?
I think that they're not
As soon as it's over.
Yeah, but you get